The basic parameters of the waves. The parameters that explains a wave are the wavelength, the period of the wave, its frequency, and the amplitude. So let us first discuss what is a wave. Any periodic disturbance created by an oscillating source that travels through some elastic medium or space is called a wave. For example, if we periodically move up and down a stretched string, so a wave pulse or a wave travels through it. Basic variables, the wavelength. The wavelength is actually the distance between any two adjacent identical points on a wave. For example, the distance between two adjacent crests or troughs on a transverse waves is said to be the wavelength. The period of a wave. The time between the arrival of two adjacent waves at a particular point is called period T of a wave, or you can define it as the time during which a complete wave passes through a point in space is said to be a time period. Actually, this is the time during which one wave is created, or this is actually the time period of oscillation of the source. Frequency, this is the number of waves that passes through a point per unit time, and frequency of a wave is actually the property associated with the oscillatory source that produces the wave. Amplitude, it is the magnitude of the maximum displacement of a particle of the medium from its equilibrium position. So we are surrounded by many types of waves, like the sound waves, the electromagnetic waves, the water waves, and so on. We can control these waves to transmit energy as well as to convey information from one place to another place. Types of the waves. Waves can be classified in two ways. Number one, with respect to the medium with which the waves travel through. So, for example, there are some waves that need an elastic or material medium to travel through. Such type of waves are known as mechanical waves, while there are some waves that can travel through the material medium as well as they can travel through the free space, where it means that these waves require no medium for the propagation. They are known as electromagnetic waves. So the light waves, all the light waves are electromagnetic waves. The second way in which we classify the waves is on the basis of the motion of the medium. In some waves, the particles of the medium oscillate perpendicular to the direction of propagation of the waves. Such type of waves are known as transverse waves, while there are waves in which the particles of the medium oscillate parallel to the direction of propagation of the wave. Such waves are known as longitudinal waves. So the example of longitudinal waves is the sound waves, and example of the transverse waves is the waves on a stretched string, the electromagnetic waves, and so many others. So here the figure shows a transverse waves established on a stretched string. Here you see the lambda. This is the wavelength, and the distance between any two adjacent identical points is said to be the wavelength. For example, over here you see that the distance between this and this crest is one wavelength, and similarly the distance between this crest and this adjacent crest is one wavelength. Now we consider we are going to explain a particular type of waves, the traveling waves, and we take a transverse wave along a stretched string. So in figure here a portion of a stretched string has been shown through which a wave pulse is passing. The wave is somewhere produced at the left side of the string, and that is traveling to the right. So consider a pulse that travels to the right with a constant speed on a stretched string. As the pulse moves along the x-axis of the string, the transverse displacement of the string is measured along the y-axis or the vertical axis, or to the direction perpendicular to the propagation of the wave. Figure 2a represents the shape and position of the pulse at time t is equal to 0. This shows the pulse at t is equal to 0. As time passes, the wave travels to the right, as this one. So after time t, the wave has arrived at this position. Now at time t is equal to 0, this point P had a vertical position 0, that is, it was on y is equal to 0 axis. Its displacement was 0. After time t, its displacement is non-zero, that is some arbitrary say y. So a non-zero y is this, but the shape of the wave is the same as it is going to the right. Such type of waves, or the shape of this wave, should be represented by some mathematical function, which should be the function of position as well as time. So we write it as y of x t, or y is equal to f of x and t. So as the wave propagates with the speed v, travels to the right a distance vt and time t. As we know that the distance covered by some something that travels with a speed v in time t should be vt. So the wave travels a distance vt in time t towards the right. And if the shape of the wave does not change with time, so we can represent such a wave is measured in a stationary reference frames having its origin at the O or the 0 as shown in the figure, this figure. So such a function should be of the type y is equal to f of x minus vt. And if a wave travels to the left along a string with a speed v, so that should be represented by f of x plus vt. For any given time t, the wave function y as a function of x defines a curve that represents a snapshot of the pulse at this time. This curve is equivalent to a snapshot of the wave at this particular time t. For the pulse that moves without changing shape, the speed of the pulse is same as that of any feature along the pulse, such as crest shown in the figure. That is, we would be moving along that crest. So to find the speed of the pulse or a wave along any direction, we can calculate how far the crest moves in a short time dt and then divide that distance by the time interval. To follow the motion of the crest, as we have shown a crest in the last figure, so if we stick with that crest, we have to take that x minus vt should be a constant in f of x minus vt without taking into account the individual variations of the position coordinate or the time coordinate. We must require that x minus vt should be a constant. This expression, that is f of x minus vt, represents the equation of wave motion of the crest. If at t is equal to 0, the crest is at x is equal to x prime. After time dt, it will cover some distance, and at the new position of the crest will be x is equal to x prime plus v dt. So the distance covered is thus the final position x prime plus v dt minus the initial position x prime, and this yields dx is equal to v dt. And we can determine the speed of the wave from this equation, dx is equal to v dt. So divide both sides by dt, we get v is equal to dx by dt. This is the speed with which the wave propagates, and this is actually the phase speed of the wave, and this v is independent of the position and time. Although over here we see that v is equal to dx by dt, but v is independent of the x and t parameters, and it only depends on the properties of the mechanical properties of the medium through which the wave travels.